Hello folks, welcome to what's going to be a boring talking video about electronics. Health warning, don't watch this. And the subject matter is going to be our MG ZS inverter from our drive unit and our Openinverter replacement logic board. When we last looked at this particular project, you may recall we were using this little guy here, which was a very simple breakout board that I made up to allow me to connect to the fine pitch ribbon cable, which goes from the OEM logic board down to the IGBT controls and so on here. So we were able to connect into that and switch things on and off and read various signals. So since then, haven't been standing still and have actually got our logic board design done. So we will go and have a look at that on the office computer and go through it in some rather boring details. Okay, so what we have here is our original OEM logic board that you'll have seen in the last episode for our MG ZS drive unit inverter. So as you see, I have lots of wires and so on soldered on this because I was doing some reverse engineering work, and now have a point whereby, as you can see here on the screen, thanks to KiCad's very impressive 3D rendering of a Openinverter replacement logic board that I've designed to replace this guy, so that we'll be able to use these MG drive units in conversion projects. So what I'm going to run through with you here today is going to be kind of pretty much, I guess, not particularly interesting to most folks. It'll be a little bit of the electronics that we've on this board here, and then hopefully in the next episode, when we come back to this, we will have some prototype boards made up and be testing them and maybe even seeing that drive unit spin for the first time. But before we go down that road, we need to have a look at the design of this board here. Now, this is it's not the first board that I've designed using KiCad, but it is the first motor control board that I've designed using KiCad. So bit of an old dog, new tricks scenario here, folks, because up until fairly recent times I was pretty much determined not to go learning another PCB design package. I'd been using Design Spark for a long time. The reason that I'd gone to Design Spark at the time was that I had learned EasyPC in work. Design Spark is based on EasyPC, and it was also free and unlimited, and so it was an easy enough transition for me. And with these packages, you tend to build up libraries of your favorite parts, layouts and things like that. So changing from one to the other is it's quite a painful process, not just on the learning curve for the particular package, but then you lose all the kind of legacy design work that you have previously done. So, but made or at least making in present tense the transition here to KiCad. One of the big reasons that kind of pushed me, gave me that last little nudge, was that Design Spark has started to become one of these things that only works when you're connected to the internet and so on, and you know, not gonna go Lewis Rossman on you, but yeah, I don't particularly like things like that. So here we are, KiCad, and we have our MG ZS logic board. So let's have a quick look at the schematic, and we will run through this in kind of moderate detail. I'm not going to try and make this an electronics tutorial, nor am I particularly wanting to get hugely in-depth into things, but basically the Openinverter system is comprised of several blocks here. So I tend to have my schematics for more complicated things divided into blocks. I know some people use sheets and link to sheets and things like that. I'm not too much a fan of that. I prefer to be able to see it all on one page, but have it divided up into blocks where I can see in kind of easier to read, I find anyway. So that's what we're doing here. So we can then zoom in on a particular block, in this case here, the microcontroller. This is the heart of the whole thing. It's an STM32F103, and this little guy, for all the, I guess, sometimes the negative comments that I hear around using a part of this age, it's an incredibly capable part, and not least of which it's capable of running field orientated control for a full-size motor. It can run, I mean, I've ran the Model 3 drive unit with this thing, so yeah, it's very capable. And even recently now, one of these parts is capable of running the CCS charging process, so you know, I don't have any problem using a part. So this is basic Openinverter layout here. We've our power supplies, our reset circuits, activity indicator LED, crystal oscillator, and various supporting components. The next part then, that's pretty much plain Openinverter, is the hardware overcurrent circuit. So that basically monitors the current sensors, and if the motor phase current exceeds the set point, this is an entirely analog circuit here, so it will be very, very fast and will catch that and trigger the PWM shutdown on the STM32. So this is again simple, old school parts here, but works perfectly well. We also here, in the case of the MG, we bring in these two guys here, int BL and int BH, which are the high and low side hardware fault lines from the IGBT driver board. So if we get a fault from any of our IGBT drivers, be it under voltage, over voltage, desaturation detection, anything, we get a hardware line here, and they're basically ganged together by this gate, and that will also trigger the shutdown of the PWM. So pretty straightforward there. Wi-Fi module, I use these WeMOS D1 parts now. I went completely away from the Olimex parts. I've explained the reasons for that in previous videos, but these guys pretty much work really well. So that's our Wi-Fi. current sensors on the MG are very straightforward as well. They're the typical, what is it, 2.5 volts analog in the at zero current, and we go above and below that depending if we have positive or negative current flowing through that particular line. The MG does actually have 3 current sensors. Openinverter only needs 2 of those, so that's what we have hooked up here. We have temperature sensor from the motor, so one of the things that we'll be doing is kind of working out the temperature resistance curve for this. So these resistor values here are really only placeholders. They're just here to let me get the board made, and then I can fiddle with them, and when we eventually come then to release the board, we'll have the correct values in here and something working. With our CAN bus, pretty straightforward, just CAN transceiver, optional termination resistor here with some solder jumpers, and also introducing some ESD protection on the CAN bus now, because future designs, this one included, that I'm doing, I can't say when, but I will be subjecting them to the the R100 EMC testing. So that's pretty brutal on kind of pulses and things like that. So we're starting to, everything's a learning process. I'm 15 years at the EV stuff, but the day I stop learning about it or learning new stuff is the day that I decide to do something else. So throttle inputs with dual channel throttle, potential divider here so we can detect whether the throttle is above or below the range that it's supposed to be, and so on. Very straightforward. Digital inputs here, your typical forward, reverse, brake, so your brake pedal on, and start, so your key on to the start position. One thing I'm not, and this will be the first motor control board that I've not included this on, is I'm not putting drivers on this thing for running contactors. I think we've kind of moved beyond the point where we would want inverter control of contactors, and also it can be quite problematic if certain conditions are met. You can drop a contactor out while the motor is turning, and that can cause problems with the inverter depending on how the inverter is built. So that will be absent from this particular design. There's really only 2 multi-pin connectors on this board. There's the external connector, which is this guy here. I'm using the same pin out on this guy here as the OEM, so you will be able to use, if your drive unit came with the harness, you'll be able to plug into this and maybe add 1 or 2 pins to it, and you'll be up and running, which is always preferable because I absolutely hate pinning connectors. So then we have our little high density connector, I call it, this guy here, where we connect to our ribbon cable that I showed you earlier on the inverter, and that's where we basically control the body of the inverter. If you want a simple analogy, this is the brain, so this is a Damien brain, and now it is a MG brain, so MG have now got control of me. Oh, what the hell? Oh. Weird. Okay, so where was I? Right, so that is the multi-pin high density connector thingy there. So moving over this way now, we have our main power supply. So this is where we take 12 volts in here and we convert it into the lower voltages, and indeed in this case one higher voltage than the 12 volts. Again, preparatory work here for rather brutal EMC testing. Includes the addition of a gas discharge tube, suppressor here on the input, several bi-directional TVS diodes both on the 12 volt and 5 volt lines, actually a unidirectional one here on the 5 volt line. So this particular circuit here gives us our 5 volt bus, if I can get my head out of the way. So this is our plus 5 volts. That is converted down then to plus 3.3 volts by just a passive, or not passive, like what they call it, dissipative linear regulator. And then it turns out that our gate drivers require a plus 30 volts supply, so we have a booster converter here based on this TPS 5534 part that takes the 12 volts in and gives us a plus 30 volts. So that's our power supply section. Now the high voltage bus measurement on this inverter is a little bit strange. Mostly they're straightforward analog signals. In this case here, it's not. It is a PWM signal that is generated, believe it or not, by the very same LM2901 comparator that we use here in the overcurrent circuit to create a 1 megahertz square wave signal that is then PWM modulated by the measurement of the high voltage bus. That is then fed through a digital isolator and appears here for us to process it. So I'm going for a pretty straightforward approach to this firstly to see if we can actually do it. So we're going to take our signal in, we're going to feed it into a Schmitt trigger buffer, which will just clean it up and make it nice and square for us, and also give us a little bit more drive capability coming out of this guy into a two-stage passive filter. So we'll see if we can passively filter that 1 megahertz signal down to give us a reasonable approximation of the high voltage bus. I'm not sure if this approach is going to work, and again, this is why the design of these boards typically goes through several prototype stages, so we'll give it a shot and we'll report back, and yes, if it doesn't work, you can tell me I've done it wrong. So this is another part here now that imagine is going to get a few comments. Gate driver power supply. So we know that here we provide our gate driver board with a plus 30 volts supply, but it also requires a control signal, and the control signal that it requires is 132 kilohertz with two opposite signals, so when one high, one is low, and so on. And also there has to be a little bit of dead time in there. I've seen it vary from the OEM board between about 5 and 7%. So we have a rather old school circuit here that I have prototyped and seems to work on the bench, so we'll see if it works out for us here in real life. The oscillator part is based on the venerable 4047, which provides us with our 132 kilohertz signal. Now the 4047 does produce, as you'll see here, a Q and a Q bar output. So it does produce those two signals that we would need. So in theory you would only need this chip and then feed your two signals from here. Sadly though, there is no way within the 4047 to provide dead time in between those two signals. So we need a little bit of external circuitry to do that. So we have a 2 input NOR and a 2 input AND gate and a little RC timing circuit here to provide that. And once we get those two signals, then we just buffer them again before sending them out to the IGBT driver board. And this then combines with the 30 volt supply and gives us our isolated supplies for our 6 gate drivers. So getting down now quite near the end, you'll be pleased to know, is our gate driver interface. So what do we have here? So first part's pretty straightforward. We've a 74573, which is just a transparent latch. So what that's doing in this case is it's taking the 6 PWM drive signals from our STM32, which will be at 0 and plus 3.3 volt levels, is bumping those up to the very same signal but at a 0 and 5 volt level, which is what our gate drivers require. So that uses up 6, so D0 to D5 of the channels on this part. And you'll then notice we're using D6 and D7 here for SPI clock and SPI MOSI, which we're then sending up to our gate driver PCB. And then we have our MISO, so this is the data coming back from the gate driver SPI. So here we're providing clock and data to the gate drivers, and here we're seeing data coming back from the gate drivers into just a simple potential divider, because again this is a 0 and plus 5 volts signal, and we're translating that to a 0 and plus 3.3 volt signal for the STM32. So hang on a second, I hear you say, do we have SPI signals going to our gate drivers? And yes, we do. So very Model 3 like. And we do indeed have to communicate with all 6 of our gate drivers. So that presented a little bit of a problem for us, because we then need 6 chip select lines, because we need to address each gate driver separately. And if we have 6 chip select lines, that would mean then that we would need 6 lines from our STM32 to provide those chip select signals. And sadly, we don't have 6 spare lines on here that we can use. However, we do have, I managed to kind of work it out so that we would have 3 chip select lines available to us. So these guys here. And if we feed them into an old friend, a 74238, some of you may be more familiar with the 74138, which was typically, well, is, I guess still, typically used in address decoding in computer systems. The 238 is, if memory serves, the non-inverting version, and the 138 is the inverting version. So what we do is here we can basically apply simple binary count on these lines here, and then this guy will select one of the 6 chip select lines, bring that high, and enable that particular part so that we can talk to it and get data from it. So what data would we want to share or receive or send, you may well ask? Well, there's some configuration data, so setting things like dead times and so forth. There's also then monitoring, we can actually monitor quite a lot of information from these gate driver chips that they use here. Unfortunately, have managed to dig out the information on how to communicate with them, but that will be a topic for a whole other video, folks. Anyway, what they also do on this gate driver board is they have 3 IGBT temperature sensors, and they decided that the best way to get that data to the world is to have it read by an isolated analog to digital converter on the high voltage side of the 3 high side gate drivers, digitize that information, feed it across the isolation barrier, encode it in 1 megahertz SPI format, and feed that back to us. So we will be actually reading the heatsink temperature by SPI in this particular application. So great fun. But there's quite a bit of stuff in there too that may or may not be useful to us. So we will have SPI comms with our gate drivers. So that is a brief overview of the actual circuitry. We'll have a brief look at the PCB design here. Again, pretty straightforward. As I said, I'm still learning the KiCad way of doing things, and building up the libraries and all that kind of thing there. So all my boards for a long time now, I've done them as 4-layer boards. So you have a top signal layer. So if we were to zoom in here, you'll see we have a top signal layer which is in red, a bottom signal layer which is in blue, and we've got 2 internal layers in the board then. One of them a ground plane and one of them for plus 5 volts. So if we were to turn those on there, you'd be able to see them. So for example here, if I was to zoom in on these 2 capacitors, you'll see that they have ground connections here, and that they're dropped down into the ground plane here, which is in this brown color by a via. And if we were to go, let's say, around to our power supply here, you would see we've a plus 5 volts connection here, and they're dropped by a via down to the plus 5 volts plane, which is this kind of darker green color here. So that provides us, it does 2 things for us really. The first is that it provides very good EMC characteristics, both for emitted and susceptance. It also makes the board layout a lot neater, because we're not trying to have pores and all kinds of things going on in there. Makes us a lot less susceptible to ground bounce and things like that. The cost difference these days, it used to be huge, you know. You kind of, you know, when I started out, it was single layer PCBs were the way to go, and we'd have wire links, and you'd always be trying to minimize the number of wire links and the length of them and things like that. But nowadays, you know, 4-layer PCB, there's virtually no cost difference for a 4-layer versus a 2-layer boards. And I guess the final thing that is worth mentioning on this, because I'm not, you know, I'm designing these things, I won't say quite in isolation, but I don't have the benefit of peer reviews of designs and design processes and all that kind of thing. So if I can if I can do things along the way that will not mask problems but potentially eliminate causes along the way, then I tend to try to take those particular routes, and I've always had good success with using 4-layer boards. So finally, you'll be glad to know, we'll have a last look back then at the 3D view. Thing that KiCad really stands out for me is the quality of the 3D view. It's world better than the likes of Design Spark, which looked like, you know, something I did with a crayon when I was 5, you know, just. But anyway, been able to see the board, being able to see a high quality 3D rendering of the board is, yeah, it's quite amazing. You know, in the space of a short time, we get this from using rub-on transfers on bare copper board. And I'd always do them back to front, of course. So you can see here that, and we can see here that, like I said, I'm still learning this. So you've a lot, like, great view there. You can look into the board, so you can kind of compare. You know, you can say, well, there's our OEM board. You know, so there we can see the bottom of it. We can see our pole locations and so on. I mean, one of the things that's going to, you know, even if you know nothing about electronics, one of the things that's going to jump out at you is you're going to say, well, hang on, there's a lot more things on this side of this board and a lot more things on this side of this board than there is on this one, and that is indeed a fact. But you can see here, this is what we're going to have pretty soon. We'll be getting some of these guys ordered, and let's be honest, right? See how many mistakes I've made. So let's start a pool. Okay, how many mistakes have I made here? I'm gonna put myself down for 5. Yeah, I think there'll be 5 mistakes on this board. So let's see what we get. Okay. For those of you that may not have watched some of the original episodes, this is our MG ZS drive unit here. Inverter bolts on the top and connects to the motor here, and our drive shafts actually go through the center of the motor here. So it's quite a compact little unit, and we're going to have our Openinverter control working on this guy pretty soon. So that's it, folks. I hope you are sufficiently bored by that incredibly boring episode. Be sure to take this as an opportunity to unsubscribe. Do not share this nonsense with your friends. They won't be your friends anymore. Also, do check out the links in the description for the Openinverter forum and wiki and other people's more interesting channels, not mine. I've also put links in there for PayPal and Patreon, just so you can avoid financially supporting me, so that I don't spend your hard-earned cash on stupid projects like this. So, with that being said, I will be heading off pretty soon to order some prototype boards from our friends at JLC PCB. And once we get some of those boards in, hopefully we won't be bored by them, and that they will actually allow us to spin up the motor. And no doubt, as I said, there'll probably be some changes and revisions and so on before this reaches the GitHub and the web shop and so on. So as I said, be sure to tune out so you don't get exposed to that. So until next time then, happy KiCad tracking.